as also the slide says, my name is Lazaros Nalpantidis. I'm working in Aalborg University, but strange thing is that I'm not in Aalborg, I'm here in Copenhagen. We have a campus here. As Sebastian was nice enough to say already, I'm working with robots. I'm with the Department of Mechanical and Manufacturing Engineering, so my perspective is quite different from the perspective of most people in the audience, may I assume. And that gave me a difficulty in preparing for this talk, just because I had to adjust the level of technicality, or I had these questions about how to present things, and I was afraid that many of the things that I will try to say, you might strongly disagree. Feel free to interrupt me, feel free to correct me. I am not expert when it comes to structural health monitoring. I'm an expert when it comes to robotics. And I think the outcome of this talk will be that there are a lot of things happening in the robotics community. Robotics technologies are expanding rapidly lately. And there are a lot, I'm sure, that's happening in structural health monitoring and related topics that we roboticists have little to no clue. And the market out there wants a combination of those two. And hopefully this talk can serve this purpose exactly, to try and bridge those two communities, build synergies, and see what's possible. A little bit about myself. I'll skip through that. Sebastian already said most of them. I was educated in Greece. I did my postdoc at KTH in Sweden, came here, and I'm continuing my career here now. I'm part of the lab that we call Robotics, Vision, and Machine Intelligence. We are a bunch of people, around 10 people right now, still expanding. We used to be 3 people some 3 years ago. We are funding our research through European, and mainly European, and some national funds. That's the link of the website, if you want to see. That's how our lab looks like pretty much. We have some robots on wheels that we call mobile manipulators. We have some robots on fixed basis. Robots on bigger wheels. That's a robot we are building for Peugeot Citroën, and that's actually a demo that has been performed in their premises in France, in Rennes. And that's also another robot that we have, a dual-arm robot called Baxter. Our expertise as a lab is on visual sensing and perception. We are doing a lot of research about industrial robots. Drones and aerial manipulation is a topic we are active, and we are looking forward to continue being active. This is probably the topic that interests this audience most. And I think that the last bullet should be also a topic that would be of interest for this audience, even if I'm not sure if this audience is aware of it. So in robotics and computer science in general, a lot of discussion is done lately about machine learning and artificial intelligence, and how can we exploit these theoretical concepts up to some 5 or 10 years ago into practical applications. How can we exploit the possibilities opened by machine learning for solving real-world problems, other than playing chess or Go against the human player. And I'll come back to that. So I start with a question. Does it make sense to use robots for structural health monitoring? And I'm trying to motivate myself and motivate you to follow my talk. So obviously there should be some good reasons for using robots when it comes to structural health monitoring. I'm quoting something that was said in the European Robotics Forum in 2016. So it was roboticists talking to roboticists, and there it was said that working in height is one of the top 3 reasons for fatal accidents when it comes to working environments. So there is a good reason already. Also, robots are safer, as said. They are cheaper to use than a human expert. They can be systematic and objective, and in many cases, we can have environmentally friendlier solutions by using robots. And all of those topics will be addressed again and again throughout the rest of this presentation. So, obviously, you know better than me, and I'm not very proud of this slide, but why do we need structural health monitoring? Well, since I didn't have you next to me when I was preparing those slides, I quoted Wikipedia here that says that structural health monitoring is the process of implementing damage detection and characterization strategy for engineering structures. We need to observe the system over time. We need to periodically update our observations. We ideally can use multiple sensors and get measurements of different quantities. And we need to analyze those features to determine what is the current state. One step ahead, maybe make some predictions about the future state. Is this completely wrong? Okay, so nobody shouts or nobody. Okay, good. So, thumbs up for Wikipedia. So, having those in mind, one can imagine of many applications. And again, you are the experts here, bridges and dams. I've seen robots being deployed. I've seen drones being deployed in bridges and dams, buildings and stadiums, vessels and platforms. A lot is done in the oil and gas industry. Wind turbines is a hot topic, especially in Denmark, as Denmark is the world leader or one of the world leaders when it comes to wind turbines, both onshore and offshore. Inspection of them, aerial inspection for the upper part, underwater inspection when it comes to offshore turbines. Large machinery and equipment, our good colleagues in Odense at SDU, they are deploying drones for rail inspection in collaboration with the Danish railway operator, DSB. And large pipelines is also something of interest as more and more pipes are extending from Russia to Europe and in other places. The topics that I'm going to cover are these. I'm going to talk a little bit about robots. I'm going to talk a little bit about the sensors that we roboticists are usually working, and I have a non-exhaustive list of sensors or sensing technologies that I will touch upon. And again, these are coming from the perspective of a roboticist. There should be better sensors that you know that we could put on our robots. I will try to review what has been recently funded by the European Commission when it comes to the merge of robotics and structural health monitoring, and talk a little bit about the possibilities opened by the state-of-the-art technologies, that is computer vision, machine learning, and something that we call aerial manipulation. And then we conclude, and hopefully we discuss all together. So that's the plan. Robots. There are those drones that everybody is lately talking about. And we usually have this guy up here in mind when we say drones, but this can be also something that falls within the same term. So we can have rotorcraft UAVs, unmanned aerial vehicles, or fixed wing. And obviously, fixed wing aerial vehicles can fly over larger distances, but again, they cannot statically stay somewhere and look at something. So usually, when it comes to monitoring of structures, we are dealing with this because if we find something interesting, we can just spend some more time with it. While here, you have probably already moved along the moment you realize that was interesting. So maybe you need to schedule it on the next pass. But here we have this luxury. And so focusing on this, there are different kinds of drones. You can have something that is fully teleoperated, and it's not that much different from the little helicopter I had as a teenager where you have full control, even if not on board. You have a human who has full control of what the drone is doing. So a lot of human involvement down here. And you can have almost zero, ideally zero, human involvement up there, where you have fully autonomous operation. So you just deploy it, and then you pray to God that it comes back with something sensible. And it depends on the algorithms that run on the drone that something sensible is returned. And from my perspective, you cannot achieve this ideal situation of zero human involvement without any artificial intelligence. So you need to have some tricks to discern what is interesting, what is not. While here, you can have a real-time feed of a video stream, and a human can pretty much, the drone can be the human's eyes, right? And the operator can tell, or an expert next to the operator can tell what is happening. When it comes to drones, some typical specs can be that we can have an autonomy of up to 1 hour. Those values are, those figures are indicative. It depends. You can have small drones, you can have big drones, you can have a lot of payload, little payload. But we can typically promise 1 hour of autonomous operation between charges. And that's something we are currently, as a community, struggling to solve. It's not ideal in many cases, but there are ways of dealing with it. There are ideas of, whenever we submit a proposal and it has to do with drones, you always expect the feedback from the reviewer that, okay, and what happens? It will make a nice demo, I agree. What happens in real conditions? What will happen if you want this to operate 24/7 or for an 8-hour shift? And the solution we are usually, of course, our colleagues who develop batteries, they increase their capacities every year, but that's probably not enough. So what we do is we deploy multiple robots, and while one robot is operating, the other one is charging, and then the switch shifts, and that if you have a couple of them, then you can always ensure that you have one operating. And the other thing that is lately gaining popularity is inductive charging. So the same way you can charge your phone on those new IKEA desks where you have those inductive pads, the same way you could, in principle, charge your drone. So there is a pad somewhere, the drone goes, sits there, and inductively charges itself. Of course, you could do it by wires. Weather conditions not always allow this, or yeah, it's a prohibitive factor. And what comes on top of that is that in certain places in the world, and Denmark might not be a good example here, unless for today, you can have solar-powered inductive charging base stations. So you can use the sun, and you don't need to watch those charging stations and charge the stations themselves or make sure that they are plugged somewhere. You can just put out in the wild some charging stations, sun will do the trick. Your drone will have the ability to go there and charge. So that was about autonomy and some ideas on how to circumvent this 1 hour limit. Payloads up to 15 kilos. You can have drones with exotic payloads. That's a typical value. You can have helicopters that work not on electricity anymore, but work on a combustion engine that can have much bigger payloads. That's one solution. I will tell you in a moment when I review the funded European projects that people have thought about combining multiple robots, and then you can multiply these 15 kilos by the number of robots. So you can imagine 4 drones cooperating into lifting something that is heavier than what each one of them can do. Speed is not a problem right now. We can go up to 70 kilometers per hour. We can go even faster if we want to. Obviously, that's a trade-off, right? The more speed or the more payload you want, you have to sacrifice a little bit of your autonomy, and the other way around. Today's drones are have certain features, like out-of-the-box waypoint navigation. You can decide in the 3D world, in a Google Maps environment or similar, but also with a third dimension, that I want you to go there, and then move there, there, and then press the button, and the robot will out of the box follow this path that you have drawn. Drones have sensor mount stabilization, so if the robot is moving, there are some disturbances. If the wind is blowing, there are some disturbances. We can stabilize this and get nice, sharp pictures or whatever other sensor measurements we want. We can have multiple sensors nowadays. That's typical, again, out of the box. Built-in collision avoidance, so a robot will do its best not to collide with a wall, even if hard winds are blowing. And yeah, that brings me again to the last bullet, wind compensation. We have been using drones with exotic sensors, as I told you. An example is here, a multispectral sensor, where it's used for crop inspection, and this drone is flying over, and then you can get patterns. So there are a lot of companies that flirt with the idea of putting exotic sensors on the drones and opening new markets like this. Drones for inspection usually have those protection here around the rotors. They can have multiple cameras, for example, one for the inspection itself and one for the navigation. So the robot needs to observe the environment in order to be able to autonomously move in this environment. But again, the operator is not interested in the environment. The operator might be interested in the floor here, right? So you need two cameras, one for the robot, or a couple for the robots to localize and navigate, and the real sensors that are useful for you guys that will get the measurements. And ultrasonic sensors is an old but still very popular technology here. Something that is quite fresh, this used to be some PhD students from EPFL in Lausanne in Switzerland that had this idea to put a drone within a bubble-like frame just to protect it. And the idea is that when it comes to drones, I have already mentioned 2 or 3 times that you don't want your drone to hit the wall. You have collision avoidance. You're trying hard to compensate wind, any disturbance, not to hit the wall. Maybe in some cases, it's actually not that a bad idea to hit the wall. So in order to get close-up inspection, you can have those gyros that stabilize the drone inside, no matter how the bubble-like frame on the outside looks like. And then you can have a drone that does something interesting as this, where you actually want it to hit the environment in order to have as a close view as possible. So in this pipe, such a tight type, it's kind of difficult to ensure no contact, but that's kind of cool. So one can imagine other simple modifications to the basic concepts that take us one step or half step out of the box that can have very interesting applications. So pipe inspection is one of them here. So I'll now briefly talk about mobile robots and stop talking about drones. So a mobile robot looks like that. It's something that looks like a car or an autonomous car plus one manipulator on it. And people in the inspection community have used such solutions. So that's the steroids version of this, I guess, where you have something bigger. You have a crane instead of a robotic arm. And then you don't have a robotic arm on top of that, equipped with sensors that can look for cracks in tunnels. And this is something that we have been, as a community, active in for the last decade or more, actually 2 decades. What we can achieve is pretty similar to what I told you we can achieve with drones. Of course, the height is limited. But what is better with mobile robots is that we are able to manipulate stuff. Up to this point, I was telling you about drones that go and look, measure, sense. Sometimes we need to perform tactile inspection, for example, physically interact. And I had a bullet some slides ago on aerial manipulation. That's the topic that we are opening as a community that is supposed to deal with this problem. So in order to tell if there is a crack, sometimes eyes can deceive me. I need to touch and feel and maybe combine the 2 modalities to tell for sure. And that's easy with a mobile robot. Why? Because this is statically placed there. I can brake, I can have a rigid contact, I can spend as much time as I want. Standing there, touching the wall doesn't cost me any energy, right? While ensuring that a drone is fixed on the vertical surface of a wall, ensuring good contact, constant contact, it's a little bit tricky. Again, I'll come back to that and tell you the ideas we have as a community to solve these issues. When it comes to sensors, there is a plethora of them. I'm coming from a vision background, so I put vision first. We can have high definition images, we can have video streams. We lately have more and more of those 3D sensors that used to cost some 5-digit prices in US dollars, and now they cost almost 2-digit prices. So you can have something for 50 US dollars or 50 euros or similar. Of course, quality is different, but in our lab, 90% of the 3D sensors we are using for industrial tasks, also in collaboration with real companies like Peugeot, Citroën, is those 100 US dollars sensors. So we're not going for the $50 ones, we're going for the 100, 120 ones. But they are here to stay, they're becoming more and more popular, and we can have crazy stuff. So combining sensors with drones, you can have large-scale 3D reconstructions. So you've seen Google Maps and you zoom, you can have this 3D reconstruction. You can do this with your drone and your 3D sensor with whatever. And if you also happen to have a CAD model of what you're inspecting, then you can have the ideal situation from the CAD model or whatever you're using, and the 3D model captured by the drone. And of course, quality of the reconstruction is going to be an issue. So within some tolerances, you can tell if something is quite bad somewhere. I've already spoken about multispectral images, like IR and thermal images, mainly for crop inspection up to now, but also for insulation inspection. Tactile sensing is something that is hitting the robotics community the last 3 or 4 years. Tactile sensors used to be extremely bulky, extremely expensive, and extremely unstable. So the ones I was playing with back in Sweden, it was nice to work with for the first half an hour, and then the accumulated heat would drive the sensor crazy, and then you would get random spikes here and there just because it was overheated. So the technology was not mature. It does get mature year by year, and right now we have quite compact and good tactile sensors, so we can have good tactile inspection. Force torque sensors is also something that we are using a lot. I've spoken about 3D sensors, but I'm not sure everybody is familiar. So 3D sensor is something that gives us an image plus the depth. And we can mimic how humans or animals are doing it using 2 eyes. And in Greek primary school, books, there was this example with the 2 pens that it's easy to put together if you have both eyes open. It gets trickier if I only have one eye because I cannot perceive depth. Okay, I'm combining 2 eyes, 2 views to get the 3rd dimension. And that's what stereo vision is doing. We have those sensors. This is a Kinect sensor. This is supposed to ship, or it was meant to ship with the Kinect. And it turned out that their big selling community was not the gamers, but it was robotics researchers, where you have a structure light where you actually project a pattern. This is not the pattern of the Kinect, but anyway, you just project a pattern on a surface. This pattern happens to be on the infrared, so it's not perceivable by the user, but it is perceivable by the infrared camera. One of those cameras is infrared. And then looking at the deformations of this pattern, you can perceive depth. You can have time of flight, where you just send light and then you measure how long it took it, pretty much like a radar. And you have a full-blown lidar, which is now it works on works with normal laser. It's not light anymore or infrared. Tactile sensors nowadays look like this. So we can have as miniaturized ones as these ones here. So each one of those points here on the surface gives us a reading, and then we can reconstruct. So you can have readings as dense as this frame here, and then you can reconstruct the sense of touch. And then you can do accurate stuff as touching a tomato. Maybe you've seen robots failing to grasp an egg some time ago, and that is a joke, right? I mean, a robot is supposed to be something intelligent. Grasping an egg, come on, how difficult can it be? Or grasping a tomato. It is very difficult. It's easier the last 2 or 3 years that we can have affordable and reliable sensors like that. It's again, that I think has to do a lot also with possibilities open for monitoring, for structural health monitoring. Projects that have been funded. So I'm not the one opening a new topic here. Obviously, there are people who have done this already. Again, my perspective might be a little bit limited. I am a roboticist. It's very easy when I Google for something to end up on a robotic-related something. And maybe if you do the same search, you end up with another list of projects. And you can see that how biased I am. So the first of those projects is called RoboSpect. It's this robot on the crane I told you that is supposed to deliver a fully automated tunnel inspection system. This project, I think it finished like 6 months ago. I'm not sure. I haven't seen exactly what are the results. I'm not sure if they are public yet. Another FP7 project is Petrobot, where now it's in the oil and gas industry, where it has to do with inspection of pressure vessels. So robots inside vessels and doing this inspection. Obviously, having humans in a big vessel is, or a big tank is very expensive and very dangerous, right? This inspection here is also quite cheap compared to how it's usually done, because otherwise you need to have ladders and put people on heights that is both expensive and not safe. So those 2 robots are coming after a first those 2 projects are following the way that paved this FP6 project called Tune Construct, where it developed such a solution, which you can see is a modest version of what has been developed here, maybe, right? So it's a normal truck with a little crane and a robot. And it's actually pretty much the same consortium that started this, that continues with this. One partner of this project up here is, I don't know if it's Royal, it's the authority in the UK that is supposed to have a look at the tunnel grid in London. And They strongly believe that this is the way to go. It's very expensive for them to inspect all the tunnel network in London, and they think that's the way to go. And yeah. Now, that were projects that had to do with mobile robots performing inspection. Let's see some robots having to do with drones that perform inspection and maintenance. This is a Horizon 2020 project, so it's, while before I was talking about FP6 and FP7, I'm sure everybody knows those frameworks. Okay, those are the funding frameworks of the European Commission. FP6 used to be some 10 years ago. It lasted for 5 years or 4 years. And then we had FP7, and now instead of FP8, we call it Horizon 2020. So Horizon 2020 is the first thing, is the things that run actually right now. iRobi is an aerial robotic system for in-depth bridge inspection by contact. It uses a lot of sensors, robot arms. It tries to not destructively measure the depth of cracks. And now the question comes, if you have a drone, how can you do inspection by contact? One idea is that you put a lot of thrust and you are pushing the wall, and then you are ensuring good contact just by that, always having the rotors on, pretty much full speed, right? And then you're performing your inspection. But again, stability is not promised here. Maybe it moves a little bit. And you are consuming a lot of energy in order to stay statically somewhere. So there was an idea, no, before I go to that, there was another idea that a robot could have 2 arms. One arm needed to perform the inspection by touching, and the other one for fixing itself on the environment. And of course, maybe we need to intervene a little bit on the environment and make sure that there are those elements that allow the robot to find a spot to catch. Or maybe you can have vacuum suction caps that if it depends on the application, it depends on the surface, right? So you can have a lot of different solutions based on the specific application. But the idea is this: 2 arms, one for fixing the robot, one for performing the inspection. And it was found that such solutions can have reduced road closing time. That goes without saying. You don't need to perform any alteration. Right now, if you want to inspect a bridge, you need to close the traffic and then deploy all your equipment and make sure that no car passes by. While with a drone, maybe you can inspect a large part, if it's a tunnel, for example, a large part of the tunnel, even with traffic, right? And there's nothing to be deployed. You just deploy the robot, nothing else. There is this Robot Aeroworks, where some colleagues of mine are also involved, that has to do with collaborative aerial robotic workers. So I told you already that some of the problems we have as a community, we're trying to solve or circumvent by using multiple robots. So making robots collaborate. So having robots to collaborate is a difficult topic by itself, but the possibilities opened are such that give us a good argument to try it. So the idea is to use a fleet of multiple heterogeneous drones for dexterous manipulation, advanced perception. And here is an idea that a friend of mine, a colleague of mine, so back then he used to be at the University of Twente, but Matteo Fumagalli here, he's now with us, he had this idea. Now you will see a UAV hitting a wall. And it's a little bit sad in the beginning. So it's trying to hit this marker here, and it's a little bit sad, right? So it goes full speed towards the marker. If it doesn't have a good understanding of where the market is, it will just crash. Here you have a spring, and then you can absorb some of the energy. And here is the idea of Matteo, where you have a spring with a locking mechanism, where you can do like amazing stuff. I don't know how impressive this looks to a non-robotic person, but this is pretty interesting for us. We as roboticists, we tend to rely a lot on software. If you want to hit something, then the normal way of thinking is that you need to perceive where the wall is, start decelerating as you approach it, have a full stop at 0 distance for it, ideally, right? That's how you normally do it. You are basing your actions on perception. While here, you can do it pretty much blindly. This robot has no clue. It just knows that this is the direction I need to go. It just locks itself when the time comes. That is an example of how there is a lot of ground to walk when it comes to development and adaptation of robots. It's not only about software. It's not that we have the perfect platforms that can perform anything and we just need to write the correct software. Platforms themselves, they can evolve. Okay, and there are simple solutions that can make a platform much, much more useful. And there is also this AeroArms Horizon 2020 project that focuses on exactly what I was telling you, on grabbing and docking and performing dexterous, accurate manipulation with another arm. An example of this project is, I've seen that video, I couldn't find it yesterday. There is a robot that grabs itself on a tree, on the branch of a tree, and with the other arm, it has a saw chain, and it cuts. And then once it's done cutting, it has the branch, it just moves and leaves it on the pile, which is kind of impressive. So this is an example of dual arm aerial manipulation and the possibilities it opens. So you can make sure that if you want to cut the branches of those trees, you can make sure you can cut them even if people are walking beneath. That's a little bit far-fetched, but that's where we are going towards. Of course, again, this is a concept that is getting bigger in Horizon, but it started back at FP7 with the ARCAS project. Then drones were not as fancy and as not available as they are today. So they had those helicopters, the robotic helicopters, and this very expensive arm. So I am always thinking how these people decided to put this arm on this helicopter. This arm costs as much as a Porsche Cayenne. It costs something like 100,000 euros. And putting it on something that flies, I would be very afraid of. But that's what they do it. And they were using this kind of robots and collaborations and fleets of such robots for assembly and construction. So that were some projects that were using robots for inspection and manipulation. Now I want to talk to you about what we consider a state-of-the-art, or not so state-of-the-art anymore, but again, new technologies that can support people who want to perform structural health monitoring. That is, for example, 3D sensing and 3D reconstruction. You can have multiple views of the statue, and then you can have the 3D model. You can compare this model against your CAD model and perform structuring. Technology is booming here. You can have insanely accurate models. One can put the camera then on a drone and then can get models of bigger things, like this building here. So here we have a drone flying around this, and if I may go a little bit, that's the post-processing. So the drone flying around the structure has gathered something more than 30 million points. What you see is the concatenation of those, 300 million points, sorry. And each one of those 300 million points is at least 2.6 millimeter accurate. For some of, depending on the application, 2.6 millimeters might be great or might be bad. But for a drone that flies freely and autonomously collects all those points, autonomously merges them into one single model, that's pretty good, I would say. Again, technology is improving, so those 2.6 millimeters can become less, or if you are using more expensive sensors, will be less immediately. And then what you can do with this model is all the things that you see here. You can check for cracks. You can look for things that are not expected to be somewhere, but they are somewhere. And that's the robot that they used. Okay, so large scale, pretty autonomous. That was a fully autonomous thing that happened here. 3D reconstruction. And then having the model, you can perform all your inspections offline, right? Having the inspection being performed online is another possibility, but then it relies on a lot of onboard processing. The good thing about this is that, some techniques that have been lying around are still used. We call them image processing, and you can have pixel intensities, morphological operations, filtering, shape analysis like edge extraction or whatever, and I've seen civil engineers using some of those stuffs. And the good thing here is that you don't need to have any annotated data. So you can just perform your operations and then take a decision, yes, no, good, bad, without needing to have examples. A lot of people have heard they're using what is called in your community digital image correlation, which is also known to us, but under different names, strangely enough. So when I've heard the term from Evangelos, I didn't know it. When I looked it up, I thought, hey, I know those maths. I've seen them before. It's just that we call them somehow else. Indeed, there are many similarity measures. Digital image correlation happens to be one of them. But there are other ones that have some advantages or disadvantages in different cases. We have many linear and non-linear optimization techniques. We have, as a computer vision community now, techniques to compensate for different viewpoints that may have varying illumination conditions. And we can deal with this stuff. We can build a nice model out of this. But again, it takes an expert to tell in the end, is it good or bad? Or it takes an expert to infuse his knowledge a priori in the system and tell whenever you get this result, that's good. Whenever you get that result, is bad. It takes an expert. And what machine learning and artificial intelligence promise that will be able in the near future or now is that the system should be able to judge by itself. So trying to think how an expert became an expert, one can imagine that he made a lot of observations. He spent a lot of time with the topic. He trained himself. He got examples, positive examples of cracks, negative examples of cracks. And then at some point, he's able to tell, this is a crack, that's not a crack. That's a dangerous crack, that's a non-dangerous crack. Can we perform the same thing on a robotic system? So beyond sensing, how can you tell a crack on a concrete wall from sensor data? Our system should be able to learn this. So what we are doing with those machine learning algorithms, maybe some of you have heard about neural networks, all of those things. Autonomously driving cars are based on neural networks. Anyway, that's all machine learning and artificial intelligence, is that you feed your algorithm with some positive examples of cracks and some negative examples of cracks. And then that trains a classifier that is able, whenever a new sample arrives, to classify this within this class or that class, okay, as a positive or a negative example. And then you don't need as an expert anymore. You just need to gather 1 billion of those images and 1 billion of those images, which is not an easy task. But then again, you have an expert for free, which you can copy-paste as many times as you want, having him working in parallel for you for free. And that's the promise of machine learning. When it comes to what we call supervised learning, is what I told you exactly. It's a classification solving technique. Crack, no crack, yes, no, such kind of yes, no decisions. Or you can have regression problems where you can give a numerical value on something like the severity of the crack. And you can give it a numerical value of 0 to 100%, for example. Again, that sounds like really cool and really nice, but again, those machine learning, those supervised machine learning algorithms, they're based on some handcrafted features. So we need to choose what is it that we feed those algorithms with. And usually this is some point of interest, so focus on this algorithm, focus on this, that's not of interest. So it takes some human involvement in the very early stages here to tell if it's edges that it should be interested in, points of interest, texture, whatever. Another bad thing is that you may need many annotated data. I said 1 billion, that's not an exaggeration. Some millions are okay, 1 billion is even better. The more the better. A good thing, though, with this algorithm is that if you gather 1 million positive, 1 million negative, and then you deploy the robot will get a new image. That's a new example. Once it has been classified, then you have 1,000,001 here, and 1 million. As you let it play, it gathers experience, right? So a year later, you can reach autonomously this 1 billion situation. Again, if the classification is correct and its sample goes to the correct bin, that's perfect. If the classification fails from time to time, it can be misleading for the system, okay? And now there's the new trend in our community that's called deep learning that comes and challenges even the machine learning and asks, can the system come up with good features by itself without needing a computer vision expert to give it? Can you just give it a bunch of images and then it tells what is the distinctive characteristic that differentiates pictures one from the other? And that's a little bit crazy to process, at least for my mind. But evidence shows that deep learning has been successfully deployed in many problems. So autonomous driving, we had a casualty from a Tesla car some months ago, but again, autonomous driving has been possible because of deep learning. Because instead of having an expert saying, you have to watch at this thing, and this is a sign, and this is a traffic light, you just give it everything, and then it says, okay, oh, whenever something goes red, we stop. Okay, so there should be a correlation here. Then color is of interest. I should be interested in red and green and yellow. This kind of thinking. In aerial manipulation, again, it is needed because the sensors that are used for structural health monitoring need also some physical interaction, and they require contact. So aerial manipulation is an emerging topic that will be more and more of interest for all of us. I guess I've talked enough about this already, but this is a new concept that you should be able to go and fix yourself in a structure and then perform all those inspections performable by a mobile robot just by using a drone now. Okay, that brings me to my last slides. Those are questions that I had for myself, and instead of trying to devise answers, I thought, okay, as a conclusion, I will just throw the questions and then have a good starting point for a discussion with the audience. Flight duration is a problem. We're facing this problem. We need to solve it. Is it enough to perform our intended tasks? For some tasks, maybe yes. For some tasks, maybe no. We need better batteries, multiple draws, working in parallel. A big question is, I've shown you those results of the reconstruction of that tower. Are those results reliable and reproducible? We are supposed to make science here, right? So we should have reproducibility. If our results depends heavily on external non-controlled factors, then we have a problem. We are working on that. We are improving our sensors to solve that. Can we perform inspection in real time or fast enough? The results from the tower, they were gathered, and then they were stored somewhere. A software took care of them and built that model. That was not online. If we wanted to fix something, then we needed to come the next day, deploy another robot, and then perform the fix. If we could do this inspection in real time, then the moment something is noticed, we can fix it and then continue, which saves time and money, obviously. I told you about 1 billion and 1 billion images, 2 billion images. I used that as an example. There's obviously a data overflow problem. So we generate a huge amount of data. Do we need to inspect all of them? Are some of them trivial? Are some of them more interesting? Can we somehow perform what we call semantic inspection, focus on what is interesting, pay less effort in what is not interesting? That's, again, artificial intelligence that plays a role. If we want to do it autonomously, we need to have some artificial intelligence, machine learning algorithm here. And what I'm mostly interested in taking out of this visit here is what is possible if you bring together some civil engineers and some roboticists in the same room. Because the projects I've mentioned, they were overcrowded with roboticists, and they were not enough civil engineers. I don't know why. Maybe there is the counter example from your community where you have a lot of civil engineers and little robotics. But we know a lot of things are possible. You know a lot of things that are possible and might be problems for us. I think if we sit together, we can solve a lot of them. And that brings me to the end.